Um, we just want to start off. We'll start off quickly with just a little in the news thing. Just so we've kind of taken off of our car loadings and why we want to keep tabs of that. Uh, what we have here is that the originating and terminating car loads of crude oil in the U.S. And you can just kind of see, how that skyrocketed, and just in the last few years. Is one of the items that you see in the news about safety. They've had a lot of accidents, or not a lot, but when they do have accidents, they're pretty spectacular, and the types of things that make the news. So we want to try to keep tabs again, like we were talking last week, just what are the different trends, so you can that's an area that I should try to find out a little bit more. Or the message things that, the FRA is sending out, rule changes. So we want to try to keep up as, part of the industry. We want to keep tabs on what's happening in the industry, what kind of things will affect our designs, just as a general understanding of the overall railroad things. I think we've kind of stressed trying to be railroad, railroad, people or folks or whatever you want to say, instead of just designers. You want to have a good understanding of the rail industry, and we brought that up several times, is being able to just understand, and that's why sometimes people kind of, I wanted to get some experience on the railroad, have it, what are things happening from the inside. But anyway, the whole thing here is to try to understand what are the trends in the industry, and to keep tabs on them, so you can have conversations when the issues come up. You're a little knowledgeable about it. When you get a job that has something to do with it, there's something that's been. You're not going to be able to retain all the information that you get, but just like a lot of things, you're going to be able to. Oh yeah, I remember hearing something about the crude oil issues. So you have a little bit there. You know where to go look for information and keep tabs on it. I think one of the things here is that, that's one of the things that, that they're expanding. I think it's expanding quick, so they're doing it the fast-paced nature of the business, and just having a great understanding of the safety issues associated with that. What can we as designers do to improve that? A lot of times it has something to do with the rail car and not anything to do with that we would come up with, but we want to keep tabs on that and be able to in those conversations. Where we left off last week was talking about the main line. We've kind of got a lot of the different issues itemized, some of the data we're going to collect. We're going to talk about it a little bit. How do we present some of the things to get to some of the decisions made? So we want to take it a little bit further this week regarding the main lines. How are we going to do our design? What are the things that we're going to want to talk to the railroads about? And try to best thing. The way I've been trying to push on our guys is to look and ask them intelligent questions, understanding the business, so you're not asking. I kind of cringe sometimes, and so does the owners. A lot of times are very polite, but when you start I don't want to not encourage questions, but ask questions in ways that sound that you've done your homework. So do your homework. Don't just be lazy and wait for the owner to give you all the answers. Or don't be lazy and let the project manager be the only guy that's going to him or her will provide you with them information. Be a little aggressive. Okay, we want to do this or that. And ask that question is we could do it this way or that way. We kind of look at this one, but what do you prefer? So when we come up with these things, I want everybody to be thinking in those terms. There's a lot of times because there isn't, one of the other reasons is there isn't a hard and fast answer on every, all projects aren't the same. People a lot of times on intermodals kind of imply to me that, well, one intermodal is the same as the other one, and it really isn't. Everyone's got their own. A lot of the stuff is similar. on the main line. I just, it's just the main line, and you're going to run 70 miles an hour on it, and it's all the same. Well, that really isn't true, and we'll show some of them things that you have to consider. But asking the right questions and doing it in such a way that you can ask a question that make it sounds like you aren't, you're very unknowledgeable. Otherwise, you can ask a question that sounds like this guy's real knowledgeable, and he's just trying to help by the answer. So I think we want to always try to be in that latter thing, because even as polite as the owners are, a lot of times they'll answer and they'll go, "Oh boy, I'm not sure. Does this guy really know what we're doing, or he seems to be asking too many?" And sometimes it's just being lazy. We don't want to discourage asking questions. We got to ask questions, because everybody, again, there's not a hard and fast way to do everything, so there's not always a right answer, and you're going to have to get those answers from the owner, and you're going to want to be able to ask it, however, in a very intelligent a way as you can. And what I'm saying here is in no way of discourage you from asking questions, because that's extremely important. And we get into more trouble the longer we wait and not ask them questions. So I don't want to imply it that way. So what is the first thing we want to try to establish the design criteria? This is a little bit in reflection back on last week, but we want to understand the design speed. On the main line, it's even more important than it is in the yard. We also want to know what the likely speed is. That came true in a lot of situations where we want to design the track for 30 or for 50 miles an hour. Someday we might do that. But right now, most of the traffic is going to 30. So does that make any difference? And we're going to want to be able to understand that, so we, again, have the holistic understanding of the project. What are the number of trains? Are we talking about 1 or 2 trains a day or a week, or are we talking about 40 or 50 trains a day? What is the mix? We talked a little bit about that. That's why the speed is important. Is a freight train intermodal or passenger? Some of the traffic might be running at 70 miles an hour. Some of it might be restricted to 35 or 45, depending on what type of commodity that it is, or some unit trains are done that. So we want to understand what we're going to be designing for, so we understand the mix, we understand the ramifications of what we come up with. Track standards, we want to identify what those are. Sometimes we might, a lot of times we've run into that where you're designing it for one railroad, but the other one's operating on it because of trackage rights or something. So which one are you going to follow? And usually it's whoever owns the railroad is the one that you're going to follow, even though the other railroad might be operating on it. We did some of these pictures are going to show a UP intermodal terminal or access to that, and it was the traffic was all coming off of the BNSF main line. So all the main line work was done on the BNSF. So on the BNSF, we did the BNSF standards. When it shifted over to the UP, it was the UP. So you have to understand that, even though you were just dealing with UP trains coming into the terminal. We talked about capacity, double track, siding length, current and future needs. How long of trains are we going to be running, so we can, if it's single track, we have to put them away somewhere for either meet head on or allow the faster trains to get by. Switching requirements. One of the things you want to know that to understand of if you're going to have a siding, or what kind of speed are they going to have to operate under the siding or into an industry track. Some areas of the country have so much mainline traffic that the railroad doesn't want to encourage or do anything or put any more industry on that line. There have restrictions that you can't switch anything on the main line. So if you do that, you have to understand that you're going to have to build that switching capacity completely off the main line and be able to depart into those tracks at some type of speed. Again, speed is capacity, so if you're going at 10 miles an hour, it takes a lot longer to get that train off the main line than if you were being able to leave the main line at 30 miles an hour. And you have to be able to stop, so you have to anticipate all those things. Them are establishing the overall design criteria, not worrying about that one simple task or specific task that you have, but looking at the overall project. Again, just kind of following up, we want, on a capacity projects, we may want no grade crossings in this area that we are, or what impacts the grade crossings may have, what property acquisition. There's a lot of times where it would be great and it would be a better alignment if you could buy a whole bunch of property, but depending on the situation, it might be, it might take months to buy the property, it might take years to buy the property, or you might have to go into condemnation. All them things are impacting what you design because the schedule for the property acquisition might be the ruling thing. Or a permit issue. How does that impact the schedules? A lot of times it's very difficult on the railroad to avoid wetlands, for instance, because you just can't turn that fast. On the roads or a building, you just put that in a different side parcel of the property and avoid the wetlands. Usually with a railroad, because it is limited on its curvature and the ability to meander, you pretty much have to go through there. Well, so then pick the area that's going to be the least amount. If you can get a nationwide permit, that's way better than doing an individual permit, which might take years. A nationwide permit, could take months, or 3 months at the most. A regional permit, some districts have those. They might be up to 3 to 6 months, and then an individual permit, for instance, might take a year or more. On one project, we actually built a temporary bridge and built over a mile of track so they could get the track material and ballast into the yard by rail while we waited to build the main connection. We couldn't do that because we couldn't impact the wetlands, so they basically just built the bridge across the thing. So that might be an extreme. That's not something that you're going to do on all kinds of projects, because that comes with an extreme expense. But by the time we got the permit, 3/4 of this, 30-track yard were built, and if we waited until we had the permit, they would have had a very difficult time getting anywhere close to that. Utility relocations, making sure that you identify them early and identify what those relocation needs are and how long is it. Some of those utilities, especially the larger ones, they got a whole bunch of people trying to cross them. You're just one of a million that they have to address, put in their thing. A lot of times the railroad agreements are pretty onerous as far as for the people that cross. They have to pay for it. They have to do it within 30 days. Sometimes they just physically can't do that. So one of the ways they control their costs is by delaying things, and then we can keep that up, because not only are you trying to do that, but the same railroad you're working for is trying to do it in 4 other different locations, sometimes even in the same area, or another railroad is doing it, adjacent. So all them things enter into the utilities. So utilities are an extremely important thing that we want to get our hands on right away. And signal requirements, another essential thing. They have a lot of impact on your design. We'll take a few examples of that. So we're going to want to get those people involved as quick as we can. One of the other things with the signals that they have limited resources with the positive train control initiatives. Most of the signal guys are more than occupied. So sometimes it's just a matter of priorities and working on important projects on the railroad. Some of those are even getting delayed because the signal guys are working on more important projects or some other critical things. So you want to get out ahead of all these issues. We're going to take a look at a few design issues. Trying to come up with do we need access roads, for instance? How are we going to get through through an area? Here's an example. This happens to be a major lead, a 50-mile-an-hour lead into a intermodal terminal. Some of the things to to consider. What is the track speed? All these things, I think we've talked about this a lot, so I don't want to repeat myself, but I think one of the things you want to know is trying to have that full understanding, because at some point, to meet the schedule, to meet what the railroad is asking you to do, sometimes you have to, I'll call them bend the criteria. Sometimes it's just impossible to do it and meet all the criteria. So you want to have a good understanding of what are you trying to do, so then when something has to give, which parameter or which criteria will you choose to try to modify. That may not be the same in every case. There's a few that I kind of just am, and it might even, that I have, that I say, well, that one's one of the first ones to go. You want to relax that criteria. Other ones are a little bit more hard and fast, and that you don't want to. Again, you want to build up your case of, I tried this, I tried that, but to do that, what is the desired speed? They might say 50, but you might end up with 30 was probably good. We did one project on one of the day one when they were breaking up Conrail. They had a project around one of the railroad's yards, and they were arguing, should I have it 30 miles an hour or 40 miles an hour? And they're trying to, because at that threshold, some curvature and things had to, and turnout sizes had to start changing. And, the superintendent, it was a subsidiary of one of the Class 1s, but it was a Class 1 project. He basically said, all I want to see is my train going around this yard without stopping. That was his criteria. You might want to try to, so that made it, put things into perspective as, if we can get 30, let's go with 30. Let's not argue and try to buy a whole bunch of extra property and change a lot of extra stuff to try to get 40 miles an hour. Try to understand what the owner, the actual end user, is really trying to accomplish. Do we need inspection rolls? That's an important thing. Sometimes you have to buy property to get them. Sometimes what we're talking about is being able to get down to a switch. Is that a place where they're going to change crews? Because that's where they're going to hold out a train if it goes on the hours of service, or then they have to change crews. So you want to be able to get a cab to that location. Or is it just to get the maintenance away folks there? Or the signal guys, as signalized, they're going to have to get there and maintain it. The railroad is too busy, so operating too much traffic to actually get track time. I've talked to a lot of, getting on the railroad was fairly common when I was on the railroad. Currently, I've met a lot of people that we've worked for have never been in a high rail, and they've worked on the railroad for 10 years. Part of that reason is because there just isn't enough track time to allow that. They don't want to do that. So the railroads will, require inspection roads to be able to get there, so they can do maintenance, in between trains and not having to actually occupy the track. What is the side slope requirement? 2 to 1, 3 to 1. Is something else required? The size of the cut. That's extremely important, depending on how much property that you have, what property acquisition you might need, what are the soil conditions. If you can't get one of them, you have to have 3 to 1 for whatever reason, and you can't get that on the property, you might have to start looking at retaining walls. So you want to understand all that. Drainage and detention. We'll look at a few things, but whenever you're extending culverts, generally you're going to, what is the acceptable losses through the culvert? And what we've found is that a lot of times, some culverts you can just extend. Some of the larger box culverts and stuff you can't. We're working on a current project that my guess is that they were all undersized, or the development at the time of the railroad was built was such that there wasn't much runoff. Well, now we're in a situation where we're not only having it for a second main or whatnot, you extend the box culvert to accommodate that, but you also, in one case, they had to put in 2 large circular culverts to handle the flow for the extra runoff to avoid the potential problems and to meet current drainage standards. Are you in a floodplain? What are the conditions that you have. So you get all these things that you're going to have to put them, document what you have, so can you avoid it? Do you have to mitigate it? You know what those criteria is. Signal locations. Are there insulated joints? Where are the insulated joints? A lot of times our surveys don't pick that up. A lot of times that is extremely important. Just on an inspection last week, and we had insulated joints and power. They weren't power switches. Well, they were power switches, push button hydraulic type power switches that were solar powered, but it was underneath the bridge. So now they had to have the solar panels outside of the bridge. So the actual solar panel was, in some cases, over 100 feet away from the actual switch that it was working with. So trying to understand all those things and getting them on our drawings and identifying them, so you know that what issues that you have to deal with. And we're going to talk a little bit here about track centers and how to establish that here, I think, in the next slide. One of the main, I think, to get started, and there's a lot of different theories about this, or different ways. So it's one of those things that you want to make sure that the railroad person that you're working for knows how you're doing it, so they don't assume it. And what I'm talking about is we want to track that 15-foot offset from the existing main. It sounds real simple. The problem is that existing main might have been tangent, when it was built in 1880 or 1920, but it's no longer. If all the time that it's been surfaced, crossings, whatever has been done to it, it's not necessarily straight. So you get a lot of, and I'm over exaggerating these things to make a point. Sometimes, I've had some where there's been a 3-foot line swing in a relatively short area. It's supposed to be tangent track. The valve maps show that it was tangent. Everything indicated that it was tangent, but it wasn't tangent. For whatever reason, it wasn't. A poor trying to get better alignment to a turnout or a railroad diamond or something. Somebody did something at some time and got pretty far off. On the bottom, one theory, and that's one way of looking at it, is we want 15-foot centers, and you design the track that's 15-foot offset, all the way through, and just follow the things. I think in a lot of, usually you're not that far off, and so a lot of people, that's how they're going to lay it out. I don't need any stakes. It's a 15-foot offset. We'll just measure 15-foot offset from the existing track, and we'll be good. Another thought is, on the what we show above is that you have 15-foot. You do a line that's 15 foot, and assume that you're going to align or design it to that best fit line. And that top example here is that we have the best fit line, and we want that best fit line to be 15 foot off. Some of the areas on the existing ones are going to be less than 15 foot. Is that an issue? I think with 15 foot, it's probably not that big of an issue. If it's 14 and the law says that new tracks have to be a minimum of 14, you don't want the thing to be 13, 11 isn't 14, so you're in violation of that clearance requirement. At 15 foot in tangent track, if the law says 14 foot and we're at 1411, you're probably okay. Not a major deal. The way I like, and you could say that, if they spent the money to go line the main line, the existing main line, is that they could put it on this 15-foot line and everything would be good. I guess the way I prefer it is that you try to look at the existing here, and they want a minimum of 15-foot center. So in this case, we put that line at 15 foot where the minimum is, and all these other dimensions are going to be a little bit greater than 15 feet. They still have the ability to line it back to that 15-foot offset and call it good there. And I think this is really what they're generally, even though they're not saying that, that's what they're looking. You got to be a little careful. Sometimes, like on this one where I mentioned that it's 3-foot offset, you might have to, get that out there, build a lot more grade to get it over there. Sometimes these little wiggles are just meandering on the same thing, so there's no real change in the grading or anything. So you just have to evaluate that. If these things are inches, is one thing. If they end up being 3 feet, you may have to evaluate it and come to one of these other solutions. But you want to do that, and that's one of them things that I don't think you want to take lightly, and try to understand what you're dealing with. You might have situations where that best fit line, you want to, just like any other, where you try to get that best fit, you don't want to, you maybe want to throw out them real bad alignment points, just so you get a little bit better best fit line. Identifying capacity. In our yard, a lot of times we are looking from clearance point to clearance point. That's what we're providing somebody. So that's the biggest train that you can get in there from the, be it the 13-foot or the 15-foot clearance point in a yard track, and that's where it was. We entered, possibly a crossing that you might have to worry about there, but a lot of times in a yard, you're going to pull that train right up close to the crossing and call it a day. Out on the main line, you got public crossings that you're dealing with, and then depending on the state that you're working in, they may have different rules. Some want to have 250. The train has to stop 250 feet from the crossing. So that's the point that you're going to, regardless of where the clearance point is, the train can't go any distance past 200 feet closer to the crossing. In Illinois, what we have is the law says 250 feet has to be clear, but the ICC, who has jurisdiction, tries to encourage the railroad to have 500 feet clear. So when they're looking at it, what is the real clearance of that siding? It's not the clearance from clearance point to clearance point, and in some cases, it's not even the signal to the insulated joints of the signal to the insulated joints of the signal on the other end. You have to identify where the crossings are. Where is the train actually going to stop? So what size of a train can you actually get into the siding? You identify where that's. In this case here, the signal is generally going to be around, depending on all the little rules that it comes up somewhere. In this case here, happened to be a number 20, so it's about 479 feet. They wanted to get the insulated joints out of the return curve, but then to figure out what the capacity, they wanted to be 200 feet away from the crossing. They wanted to have the train stop 500 feet from the signal, so they're not pushing that. But because in this example here, the 200 feet over took precedent over that 500 feet, because at 500 feet from the signal, and we'll kind of have another example of why that turnout had to be there, because there's other issues don't really show up on this. But here's a case where the railroad wanted to be, they didn't want to have the capacity at 200 feet. That was their operating rule. This wasn't Illinois, as the example I was mentioning. On this other end, you got a lot longer, and that's the one we're really going to show how far. Why is this so far, and why did they want? It happens to be that there's a big long curve in here, and they had to deal with that. But you want to come up with some type of a schematic to identify where those switches are. So there's a lot of things that come into account on trying to figure out, we wanted 9,500. I think the answer was that they, on this one, they wanted 10,000. They really needed 10,000 was the standard for the railroad. What they were going to need was really 6,800. So that once as we started coming down to, you could do more to, you have to close one of these crossings to get more than 10,000 feet. But they were able to live with that clear length because of the operating conditions. So you started to balance all them things, and again, understanding what you're trying to do. it allowed you to make an educated determination of what you were going to recommend. You want to identify what the capacity is required. What are the planned lengths of trains? Standard. We want all sidings 10,000. So, but try to find out what they really need. Here's a standard, because a lot of times you are, like I mentioned, because of curves, because of crossings. We had another one where they wanted a 5,000 feet of tail room coming off of an industry track. Well, if they had got 4,500 was fine. To get 5,000, they would have to build another bridge across a small creek. And well, let me see. We want 5,000, but 4,500 will be fine. We don't want to build an extra bridge. So you have to try to understand that. You go through it and provide them what they want, show them what those obstacles are, and then provide the economic justification for maybe in the case that we had the bridge, maybe 5,000 was the bare minimum. For whatever reason, they had to have 5,000, and there wasn't any compromise. So building the $400,000 bridge wasn't a really problem. Impacted grade crossing. Can you get it relocated? Can you have to make it a grade separation? What are the options that you have? Can it be closed? Everybody's trying to close crossings except for the person that lives there. So what's the likelihood of getting that done? What are the sight lines to the signal? You can't, it'd be nice to put it in one location, but you can't see it from there, because of a curve or some other obstruction, and so you can't put the signal where you wanted to have it, and that might impact the cost of, grade crossing, property acquisition to get what you need. All these things, may lead you to the determination that, a shorter length might be acceptable. What are security concerns? This happens to be, in an urban area. We talked a little bit about that last time, but, are you going to need something to secure the right-of-way? The railroads are very high on security. There's a lot of places you can drive right in. In most urban areas, they don't want the general public or rail fans or whoever doing mischief around their tracks. So, try to come up with a way to secure access to the right-of-way. How are you going to handle the off-site drainage? We're going to show some pictures here, but the normal flow of the water all came across this and went right through here and down this way across the right-of-way. It don't look that way here, but we're right in here. We ended up being about a 40-foot cut. We're about 10, 12-foot cut or a little more here. So this is a grade separation over the railroad. I think it was about 15-foot cut. But you couldn't have the ditch and the regular water that through here coming through there and go down into the ditch and come back up. So this bypass ditch was included, and we actually crossed way back here. So understanding what the water flow is, especially if you're in a situation where you're going to have to make cuts. If it's up on tangent, you might just have to have the same thing back to the extra culverts or just to lengthen the culvert. Is that going to cause you a problem? What happens when the water backs up? That one area, just looking in the back, this area here, another one of those things where there's a lot of different ways we could have handled that water, but they weren't going to. The developer chose not to buy that, so they had to drain that water away some ways. So the natural flow was this way, and it had to go down on the railroad. So they took that down and rip-wrapped it down into their existing. But being able to address that, what are the ramifications? How are you going to deal with that situation is extremely important, and try to identify those problems early. We had under drains and stuff coming out of the adjacent land. They were picked up and brought down to the railroad track ditch. We're down in the bottom. We were in a floodplain, so we had to have some compensatory storage. and could also, there was another culvert that was going underneath an adjacent railroad. So we had to figure out how we're going to handle the water there, because we didn't want to spend the time to go over to the other competitor railroad and tell them or ask them that, can we put in a couple big culverts underneath your railroad? So we came up, what the solution is to detain the water and then allow the water to flow out in a controlled manner that the existing culvert could maintain the existing flow. The whole point here again is trying to understand these things early on. If these are things you kind of stumble on after you start getting down into the construction mode, obviously that's going to cause you some grief. So you want to try to be looking at what are your options. So if you have a pond and you have to buy extra property, you can't buy it, it wasn't beneficial to buy it up here in this big cut. You bought it down in the bottom where it was a little flatter, and, it was something that you could actually do. So you wear them, balance them impact. It's another, and find out the water actually flowed through there and came across and went actually underneath the other railroad on the other side over here. Here's a situation where this is a road, that road crossing. How is these tracks going to cross that? The decision was made is that it made the best sense for everybody is that that this road be closed, and it was, and then that bridge was built that you've seen on the previous slide. So everybody kind of won. The railroad didn't have to worry about that grade crossing, the safety ramifications, and the public was always going to have a clear, open path to wherever they're trying to go, instead of having to be potentially blocked by a train. Again, early coordination with the signals. We mentioned this a lot. We're going to take a look at some sketches again. But what are the site distances? Signal locations. Making sure that you have enough room for that. Are you along a retaining wall? There really isn't any place, so you have to add that to a retaining wall. Work with the signal guys. What is the ramifications of moving? It's surprising that moving a signal sometimes, 300 feet, is really detrimental to one thing or another, and it seems like it should be easy just to move that signal up there, but you don't have your stopping distance. Again, on the railroad, a lot of things don't happen. Decisions aren't made by what happens at a specific location. That a lot of times it happens, like we pointed out, miles away, sometimes even tens of miles away. You want to identify where you're going to put the signals so you can see that you have enough room. If you don't have room to put signals in between the tracks, you might end up having to have a signal bridge, or providing enough clearance here so you can put a wayside signal in between the tracks. Back here, just on the stationing control, you want to identify. That's another important thing of identifying and using the valve map, so you know what the railroad station is using, so you put stuff in the right location. The signal guys, their plans are generally follow the track station as well. So you don't want to use that arbitrary, local stationing. You want to be able to tie that to the railroad stationing from the valve map, because generally everything else is set up that. You're going to get these early designer sketches to identify, you've got a bridge here where the signals are going to be placed, so you know what stations that is. Does that lend you a problem? You're going to have, they usually will tell you, an 8x6 or an 8x10 or, it's 10 by 20 foot bungalow, hut, whatever they refer to it as. Where are the information, or what are they going to need, and where and how far out? So usually, if you're going to put in a new control point for your switch, they're going to have to do something to either in this case the start they're saying, so they understand for the grade crossing. There's a grade crossing here. On another one, there's going to be another block signal that's going to be out here somewhere. Is that in our project? Who's going to take care of the grading for that? Sometimes it's us, sometimes it's the signal guys take care of themselves. But you want to ask them kind of questions. So you want to get these designer sketches as early as possible to try to identify. What they might do is come up with, we want the bungalow over on the right side, and you say, shoot, that's a big cliff over there, and you got a big ditch that runs through here. Can we put that over on this side? And work with them to find out, and they might say, God, that really causes me a lot of grief. I can't go that far. I can't do this. And then you try to work that out. But if you wait until the last, wait till later in the project, you don't have time to accommodate them. It's easy to accommodate everybody at the, if you catch it early enough. Conceptual schematics, mainline thing. Here's a BNSF one. I think the colors are different. This is one of our early ones. The railroads are real particular now. They're trying to standardize everything. Make sure you understand what kind of color, the colors are extremely important. They don't want to have to, quite frankly, they don't want to have to look at the legend and see what you told them that was happening. They want to be able to look at it because blue tracks are always this. Red tracks always mean this. And they want that to be consistent on their thing so they can understand it. In this case, that you're signing off is a sign-off schematic. So all the people, all the right people that need to approve the plan fully understand it. There's a lot of things that they've added, what is actually happening. There's a little bit more that they normally put on these. But find out each individual railroad. You've seen a couple examples. Some of them you develop and they want different stuff on it. You want to understand what the railroad wants and what they need for the powers to be to actually sign off and approve the project. This was an early one that we built, at one location. The main lines were 83 feet apart. We started adding a whole bunch of stuff in there. As you can see in here, they start, when we added a new connection. This was that connection where we were looking at them aerials and the drainage issues. So the railroad wanted to know between all these signals. Now I got basically three main tracks because this siding was a controlled siding, so that was signalized for 30 miles an hour. The main lines were 70, but they occasionally would want to park or just park a train out in the main line. They wanted to know what it was. With all the crossovers and stuff, they could still operate and get around it. They want to have that flexibility. So the use of schematics are generally great for that. The operating guys have a hard time, for instance, reading design plans. But when we get them, schematics, they can get. I want to train from here, and I want to be able to get over here. What do I have to do, and what do I have to go around, and can I get the right signal indication to accomplish that? And they can usually on schematics, they usually can follow them fairly well. They just don't blow up. You start putting some of the details that you have. What's the clearance between the signals? But this is a case where they're going to want the trains to stop. Whatever them in this case they wanted to know what the distance was between signals. We'll deal with what length of train we can stick in there because technically, I guess actually they can put a 9,248 foot train between the two signals. That's not what they want. They're going to, depending on what railroad it is, they're going to want to have the train stop behind that signal for safety, just to make sure that they don't go across the insulated joint. But it clearly identifies what routes do I have, where signal bridges are, how far it is to different things, so the operating guys can understand what's happening, and it makes it real clear for them. We're going to want to do the preliminary sketches. Here's a situation with, got two existing mains. They're going to build a new main up here. But one of the things, this section works real good here, but because one main is at a different elevation. Is this low point, what really happened? In this thing, the two mains at one time were different railroads. They're 83 feet apart, as you can see, and one's higher, one's lower, depending on, in this 5 miles. So this is a good typical section, and it works real good. It almost makes sense. It got the low point out here where you got the widest gap. You can put an under drain, or you got your sewer over here. But the reality is that sometimes this one went down below. So this then, at 2% here, So this thing didn't always work quite that simply. So you want to identify that early on so you know what the ramifications. This one's going a lot farther at 2%. If these are at the same elevation, this one works so good because you're going 11 feet at 2%, and now you're going 45 or something. So you've got a lot lower. So that didn't really happen that way. So you have to understand what those are, and drawing typical sections to scale, trying to address what the issues that you have as you're drawing that. A lot of times, did I take that into account? What ramifications? So there's a case where you might come back. This is really what you want to have happen, but what you might have to have is come down to here is be a low point, and then you come back up or something. Whatever it is to come up, and you might ever have to have some drainage over here because you're coming down to here, you have to come up to here, and then back down to that one, so you're only going the same distance or whatever. So you want to take all those things into account, and typical sections is the best way. If you don't do anything, because nobody can see, nobody. The people that are actually doing the design are the ones that really have to catch that stuff because, the contours are hard to read on a railroad wise. Cross sections, once they get fully developed, you can see that stuff if you're paying attention. But early on, you're the one that's seeing the survey information and don't know what you are going to get. As usual, take a little long. Showing the project elements, you want to show all the elements, what areas are you going to excess property you're going to buy, so everybody can have one exact drawing that can see as much as they can on what's happening. Property acquisition, try to identify the property owners so everybody can make those decisions that they need to make. Try to do it in a manner that's as clear. Follow up something like this with little blow-ups of what you're asking for in each one of them so the property guys understand what they're needing to acquire. There's a little more detail so you can kind of see there's a cut fill line so you understand why it's out where it is. Sometimes they want to keep it as some uniform thing. If two property owners, this guy might be easier to buy it from, or hard to buy it from, so you might want to squeeze that down. But this drawing like this makes it really easy for them to identify. Come up with, here's a situation where the standard track ditch over on the side, would make sense, except for we're cutting some guy. We have to buy the property, and not only that, we have to start cutting some of his trees that they're not his tree. He planted them on the railroad right away, so he has no real right to them. But it blocked the railroad from his property, and he wanted to keep them there. So he identified it, identified what the issues were, and so what are the ramifications of moving the ditch over to the other side? Over there, you ended up having to buy more property. So them are the ramifications, but you give a clear exhibit, they can make them decide decisions. Here was that situation where you had that big long curve, you had the switch, you had to wait until you got around the curve to put the turnout in tangent track. They didn't want to, you didn't come back, and so you ended up with the track being actually a little bit further out. You wanted 15-foot track centers, but you didn't want to come back tangent and then follow the curve around because you put it more curves in there. But you do this, you understand how much you're going to have to extend this culvert. You find that, if you need a signal bridge right here, you're near the culvert because that's where you needed it to be. And so you're going to have to do something on the other side. So everybody can understand, I got plenty of right of way, that shouldn't be a problem. Well, if there's a big, if you're on a big fill, that becomes a problem. If it's a nice, flat area here, not so much. But trying to identify all the issues that you have. Making sure that we understand the CAD standards, making sure just all the typical stuff, the tech side. The railroads are very particular about what's used. On the larger projects, you want to select a CAD manager, somebody that's trying to, the CAD Nazi, somebody to try to keep everybody doing the same thing, because we all have different preferences. making sure that our naming conventions, so it's just as easy as possible to work with each other. Operating considerations, train restrictions. I think we've talked a lot about this in the past, so I'll kind of breeze through this. The grade, how much tonnage, what's the ruling grades. Keep in mind that, you speed to the whole train, so when you have slower things, the whole train has to get over it, so, the train will be tied to that restriction, for 1.5 miles or whatever. What are the switching, making sure you're not putting turnouts in, on a steep grade to where if the train has to stop to get into the siding because it's a manual switch, how is he going to stop at that if he's on a steep grade and he can't, throw the switch? So understanding your situation is important. Grade crossing. We have a section coming up on grade crossing, so I'll be brief here, but when you get multiple tracks and super elevation, you want to understand what's actually happening. If the track is flat and the road is flat, everything works out good. But if the road's on a grade and the track's on a curve, you got super elevation in there, trying to get a smooth crossing is extremely difficult. That's one of the reasons why they always, just one of the multiple reasons why you want to try to locate your turnouts or your crossings in tangent tracks, so you don't have the super elevation issue. Worry about sight distances. Most public crossings nowadays are going to get gates and flashes, I think, as a general rule. Some of the lower, we've done some that have less than 500 vehicles a day that are getting gates and flashers. The ruling grade, we talked about that before, so I'll kind of go through that, but that's extremely important when you're coming up. Don't add extra grades in there. Be careful what you're adding, especially if they're for any distance. I'm going to take a quick look here in the last minutes to talk a little bit about super elevation and curves and how we're doing that. One of the things that separates the highway from the railroad is that, as a general, certainly all in main line, you're going to add spirals to all your curves, end of the curves, in between compound curves. And a lot of times you want to provide enough length, for possible future changes. If the track is going to be 40 miles an hour, but, in the next 10 years, they might start running 70, and you're building some new alignment, you may want to make them spirals long enough to accommodate that higher speed, and you just don't put that much elevation in initially. So you want to, again, understand what the overall project is and what the future might bring. Super elevation. That super elevation is the difference between the inside rail and the outside rail. We'll look in a little more details here in a minute. But you're going to increase at a uniform rate through the spirals. It's going to be constant through the curve. It should be 0 in the tangent. It's going to be constant. So a 2-degree curve, you'll go from 0 to 2 degrees or 2 inches in the spiral, and evenly spread that 2 inches over the entire length of the spiral. And then during the body of the curve, stay at 2 inches until you get out the other one. So this, and I don't want to rush through this too quick. I don't know how many of you have looked at super elevation. It's a pretty simple concept, but it has multiple things, and for some reason we all seem to have a little trouble with it. But anyway, the equilibrium elevation, we'll just start with that. A couple of simple things. Equilibrium elevation is where basically if you're going at a given speed going around this curve, you don't feel like you're tilting very much. You just kind of feel like you're at centrifugal forces and everything. I won't get into all the physics there because I don't know it. I don't really care. The point is that at that situation, that is the optimum. If all the trains are going to go 60 miles an hour around that curve, everything is just nice and comfortable at some specific equilibrium elevation. This calculation is what you'd use. This factor, the speed in miles per hour um, squared times the degree of curve in degrees, in decimal degrees. Generally, this equilibrium elevation is going to equal the super elevation, the actual super elevation, and underbalance elevation. That's what that is. So now our task here is to get the E sub A and E sub U with what we want it to be. The E sub A, the actual elevation, most railroads are going to have a minimum. If they got a curve on a main line, they generally are going to want to put some elevation in. Generally, it's going to be a ½ inch. If it needs any elevation, they'll put a ½ inch. Some railroads we've run into actually require an inch as a minimum. The maximum actual, 4 inches, maybe 5 inches. Anything more than that, generally, it'll note that says that you need chief engineer approval. Underbalance, which is basically it's going to be not what are you not going to put in there, to make that equilibrium speed. How many inches are you going to not put in there? So one of the reasons for that is the optimum thing is because you're going to use that as for different on the wear, because the trains don't go through there always at the same speed. The world would be great if every train went through there at 60 miles an hour if it was a 60-mile-an-hour curve. But trains are going to go through there at 30 miles an hour. Some are going to go slower than that. They never should go more than that. But that's, so you have to accommodate that. As a general rule, most railroads will have that underbalance on freight railroads. You'll have to look, and we'll look at a chart here from one of the railroads. But it's generally good, as a general rule, 1, 1.5, 2 inches will be the actual minimum that they want an unbalance. The maximum unbalance is 3 inches. If you get more than that, you're going to feel, if you go too fast, that's actually putting less elevation in there than that equilibrium speed. So, like if you've ever been in a passenger train and you go around a curve very fast, you almost start feeling like you're heading towards, if you're on the outside, you're heading towards the window, or you're feeling like you're going to fall out of your seat, and that's what you're trying. You really try to avoid that. 3 inches is generally considered the maximum that you can tolerate. For a comfortable ride. The other purpose is that you want to do that because the freight trains are going to go through that curve real slow. The passenger trains and some of the intermodal trains are going to go through there pretty fast. So sometimes the curves you're going to have to balance, and that's one of the ways that you tell the difference between what's the maximum speed here that you can give for a given elevation will be determined. It'll be different for, if you have 1.5, it'll go through it slower at 1.5 than at 3, based on the equation up here. Just using as trying to identify, and we're going to do end here with a couple of quick examples. But you want super elevation. A lot of times you want to balance the two. That's another way of doing that when you're at the lower end. Use the maximum, minimum, just, discuss. The length of the spiral, there's a couple of equations in ARIMA that, and each railroad has their own, but, I usually try to use the ones in ARIMA just to check to see, to get a understanding of what each railroad's things does, and so I have a little, if I have to vary from that, why do I have to vary it, and am I still within the realm of reasonableness? On the length of spiral, using the unbalanced, one of the things you can see is just a direct correlation, 1.63 times the unbalanced times the speed. That's what they do on new construction, trying to minimize the amount of length of the spiral on existing conditions. They might use this, but you can see that one of the things that happens is if you've got a passenger train and you got 3 inches of unbalance and you're going to go 70 miles an hour, that ends up being a pretty long spiral. If you got 1 inch, trying to go through the same speed, you know, the length of spiral that you need for there will be a lot less. The equation for the actual super elevation is 62 times the actual elevation. So if you have, you know, 1 inch of actual elevations, you need to have the spiral length being 62 feet long. All the railroads, you know, have charts. You know, some railroads have 44 inches, you know, per half a inch of super. With the example at a slower speed, the example we're going to use, you know, has 31. But each railroad has their own. You're going to generally use charts, but a lot of times that, you know, it's a good rule of thumb to check with a reaman just to make sure. Follow the railroad, but, you know, check so you understand it. Spiral length and minimum criteria. You want to have a minimum spiral length of 100 feet. Is generally a minimal, you know, is your target. A lot of times you're not going to be doing that. The body of the curve, we talked a little bit about that when we were talking about maintenance, is you want to have that as being 100. And that distance between the tangents is also being 100. Keeping in mind, again, that little rule of thumb is that a spiral length, if you got a 200 foot spiral, generally that means 100 foot is inside, you know, if you had just a simple curve between the two lines, you know, you'd be 50 or 100 feet, half of it inside and outside of the curve. So you get some kind of an idea of, if you make the spiral longer, you know what impact you're going to have both on the tangent, the body of the curve, and the spiral length. So you can do some little comparisons to get you into a ballpark. Just as an example here, try to go through that. If we have a speed is at 40 miles an hour, the degree of curve that we're in is 2.5 degrees. So we got the equilibrium speed is the equation that we had before. So we got the 0.007 times the speed squared, 40 miles an hour, times 2.5, which ends up with our equilibrium. To give equilibrium elevation, we have, you know, 2.8 inches of elevation that we have. We know that the equilibrium elevation is equal to actual minus the unbalanced. So we got the 2.8 and 2.8, you know, for freight, you know, railroad might want as a general, just take a look, you know, generally they'll want 2 inches of unbalance. So you do that, you end up with 0.8 inches. That's pretty close to 3/4 of an inch. But you might say, you know, the railroad might say, you know, there's a, you know, sometimes you use a little judgment there of sometimes they want to, you know, do it only in half-inch increments. Sometimes they'll allow 1/4. You have to depend on the railroad, but there's a case you'd usually go up to the upper one. So this is above 3/4. So the next logical thing in 1/4-inch increments or half-inch increments would be a 1-inch winch. So now we want to take a look at the length of the spiral. So we're going to have 1 inch of actual, and we're going to have, you know, a little bit. Our target was 2 inches of unbalance, but so the unbalance, you got the 1.63 times the unbalance times the speed. So you do the 1.63, 2.8 minus the, you know, we got 1 actual, so we end up 1.8. So, you know, though our target was 2 initially, but that's what the balance is here. So times the, you know, the speed ends up with a 117-foot spiral. The length of spiral for the actual elevation, which is 1, ends up to be 62 feet, not 62 inches. And then the spiral, you know, length required is the largest of those two. So a lot of times what you'll do is, you know, 117.4, you might round it off to 125. If that causes you some grief, maybe you're going to want to do it at 120 or 118 if it makes a difference in, you know, the criteria that we used previously about trying to be, you know, trying to get a 100-foot, you know, body, 100-foot curve. So, you know, so we got the spiral length is 100. Now you want to look the circular curve. Was that over 100? Was the tangent between the two, you know, reverse curves? If that was the case, you want to have that a minimum of 300 or whatever the minimum was that you were using. Just here's another one using a CSX chart. Same problem. We'll look, I just jump back here. Some of the things you got are 40 miles an hour curve. 2.5 is the degree of curve, so where they intersect the CSX, they're going to say not 1 inch, not 2 inches, but they want 1.5 inch, and they got 1.5 inches of unbalance for speeds, to and including 60 miles an hour. So if we're under 60 miles an hour, we're going to want 1.5 inches. So they come up with what they want is 1.25. The other criteria that they had for minimum spiral length is up to 50 miles an hour. They want 31 feet per every half inch of elevation. So back to our equation. So the actual from the table was 1.25. The equilibrium was still 2.8. That didn't change any. But we have, they took just checking with our equation was 1.5. Came up with 1.3. So you can see that the railroad, they took 1.3 versus 1.25. In this case, their standard, they wanted to go to 1.25. Length of spiral was 31 times the 1.25. A half. They want 31 feet for every half inch. So there's how many halves are there in this 1.25. So it ends up being 77.5 feet. So on the CSX, they would tell you that a 77.5 foot spiral would be good. We had the exact same curve. We just calculate a little different. What we calculated before was 117 feet. The unbalanced spiral length was based on rider comfort, the unbalanced part, and not so critical to the freight side. So if this area doesn't have any passenger trains, or even if it does, the CSX in this case has decided that we don't need to have that one. I usually try to do that calculation so I'm aware of, what their criteria is. So I understand a little bit that it's a little different. Why is it different? I can make them evaluations. So if we need to make some adjustments, or if they want us to do something special, well, we can make those corrections. Vertical curves. I won't go into that in real great detail. We've looked at that a little bit before, but the minimal vertical curve length is 100 feet or 3 times the speed. You want to optimize grade. You're not going up and down. You want to have constant grades as best that you can. You want balance the profile design. Coming and going, the train has to go in each direction. So you want to minimize it. If you can avoid it, you don't want to have steep grades going in one direction and the opposite in the other direction. So eastbound trains can get by with less power. You have to put more locomotives on going east. So if you avoid that stuff, that kind of things, you want to make sure that you take that into account. I think this is the last thing, so we'll end up here. There are a couple of different, the old version of doing the vertical curves is that you did the difference between the different grades that you had divided by the length of the vertical curve in station. So if it's a 200-foot vertical, the length there would be 2, and what you're going to be looking for is a 0.05 rate of change for sags and 0.1. And what you end up with that is extremely long vertical curves to meet those criteria. We've done some. I use this as a criteria. You have to always check with the railroad, but I had one railroad guy that I trusted. We were doing a lot of undercutting under bridges to get more clearance. And one of his rules of thumb, instead of following that, he kind of relaxed it. When he was running 25 or 30 miles an hour, he wanted to try to get that rate of return under 0.25. Partially due to passenger train stuff and sometimes actually transit agencies, they wanted to come up with a different a more relaxed version of the vertical curve, and they came up with this equation, which I won't go into the in all the detail, but they have a constant factor in here. The acceleration, they're going to make a difference between freight and passengers for this A value. The K value is given, and then it's a matter of what's the speed and the difference in the grades. This is going to provide you a significantly shorter vertical curve, and it fits in a lot more. It's more practical. I think this one is at least I've never heard the definitive answer of why that is, but most people it goes back probably early on. Railroad is just historically doesn't want to change something. A lot of times it's there for a reason. They kind of came up with that based on situations, and sometimes you change things at your peril. It's little subtle things that nobody just can quite put their finger on. So when you change it, it starts impacting what you're actually trying to do, and without knowing it. So it was a struggle to get this, and eventually the railroads adopted this with that A factor, and that's how the compromise that they made to try to get that shorter. So if there are any questions, or there's a couple of the items there that would be a lot better, go into a little more detail. The super elevation, for instance, is relatively pretty simple and straightforward. It seems like it, but you can a lot of different type of answers that you can get if you increase the try to optimize that. Or what's the between the unbalanced and the actual, what is the most optimal to get for the length of spiral that you're going to use with the length of curve that you have to fit in the situation that you have. And a lot of the times, especially in the urban areas, we're asked to violate that, and having a good understanding of what you can and can't do there, instead of just following the rules or their chart. A lot of times the railroad, if you can't meet in this case we were showing a CSX, if you can't meet the CSX one, you certainly want to do that. If you're working for the CSX, you want to follow that one. If you're working for the BNSF, you want to use theirs. The UP, you want to use theirs, and NS the same. But if you can't meet that, one of the things is to use one of the other railroads. If it's, even though the UP doesn't want to use the CSX standard, it's a legitimate standard. And then if you're going to, cut that back, and use that one, to help justify your argument. You might go back to ARIMA because of the situation. We think this is adequate and will do you a good job. But you want to first. You want to exhaust all the possibilities of eliminating, that if you can't use their specified standard, you just don't want to do it because it's easier or it's cheaper. You want to do it, or just want to. If you can do it, follow their standard. If you can't, now you're going to have to make some value judgments, and you want to try to manipulate. So that's one of the areas that you can play around a little bit and get different answers. And it's surprising, what is the logical, that actual, I had in one case where we were going through a temporary curve, and it was right at a place where, we just know in our gut that, they had to get permission to get onto another railroad. So they were always going to almost have to stop to get permission to get onto the main line. Well, it was designed for 50 miles an hour. So that required about 4.5 inches or 3.5 inches of elevation, I think. Temporarily, we're going to have a grade crossing in there with 2 tracks. 3.5 inches of elevation makes for a pretty rough crossing. Knowing that initially all the trains were generally going to be probably going to have to stop there, let alone go 50 miles an hour. Is there any, you can make it so that this, by adjusting the spiral lengths and the amount of super elevation you put in there, you could get, fairly close to what they wanted with a lot less spiral length in there. And the railroad initially said, absolutely not, we have to follow, there's no reason we can't change it. But when we actually built it, they just did put, some somebody got in there and did say, okay, all the trains are going to stop here, so let's put in less elevation because that's detrimental to the track. So you want to be able to understand what's actually happening, what are your options, and remain flexible so you can explain that to the owner if you're going to ask for a variance. So. Any questions? If so, I guess I was back to that. If there are any questions and nobody wants to ask them now, certainly don't hesitate to send an email or we can follow up with that. So, thank you.
Thanks, Dave.
Excellent.